so let's get started. So today's the second lecture on proof theory foundations, and I'm going to talk about propositions as types, which goes back to two key papers, one by Curry in 1935, and then by Howard in 1969. I will talk about it in the style of Howard's paper rather than Curry's paper, even though they're both worthwhile reading, quite interesting. But before I get into that, I thought I might talk a little bit about the homework because I got a lot of questions. So it would take some time out of the lecture, but it may still be time well spent. Is that okay with everyone? Okay. So there were a number of entailments, and the most questions I got was one in particular. Which was, make sure I got it right. Okay, so we want to prove this entailment, A or B, and A or C proves A or B and C. Okay, so that's people who had most trouble with this particular entailment, or maybe they had trouble with other ones, but they didn't get to them. Okay, so that's how far, that's what I got the questions on. Okay. So let's informally first think about why this is true, okay? And then let's see if I can talk you through how to actually write down the proof, right? Okay, so why should this be the case? So we want to prove that A or B and C, this is what we know. So because this is a conjunction, we know this part and we also know that part. So we have A or B and we have A or C. Okay, so far? Okay, so now we can distinguish cases because we have A or B, so we know A must be true or B must be true. If A is true, then the disjunction is true because that part is true. That's easy. In the other case, P is true. Okay, so now we know B. Okay, we still know A or C. We haven't used that yet, so let's distinguish cases on that. If A is true among these two, then we get A or B and C because A is true. If C is true, then we have B and we have C, and together they form B and C, so the disjunction is true because of that. Okay, does that argument, everybody buy that? Okay, so the only issue is how do you actually turn this into a proof in natural deduction, right? Intuitively, this is what holds. Okay, so how do we start? So we start at the bottom. We're trying to prove A or B and C. And we have this assumption sitting somewhere out in the ether, okay? Maybe exactly here. And A or C. Okay, so now the general strategy in doing this kind of natural deduction proof is that we only use introduction rule from the bottom to the top and elimination rules from the top to the bottom. Okay, so that's the basic strategy. We apply elimination rules to something that we know, and we apply introduction rules to something that we're trying to prove. Okay, does that make sense as a strategy? Okay, now it turns out in the next lecture I'll prove to you that this strategy is complete. So if you only apply introduction rules from below and elimination rules from above, you will always be able to find a proof if there is one. That's a surprising fact, okay, if you haven't heard this fact before, but it is true, okay? So let's look at this. So our choices are the following. We could apply an introduction rule here. Now there's two possibilities. We could try to prove A by itself, or we could try to prove B and C. Okay, but A by itself doesn't hold because our assumption is much weaker than A. So we can't apply an introduction rule here, period. Can we try to prove B and C? No, because we know there are some cases where A is true and we don't know B and C. So we can't apply an introduction rule here, we're stuck at the bottom. We can't apply an introduction rule and try to prove that either from A or from B and C. Make sense? No hope. So we have to apply an elimination rule here. Okay, well, what eliminations rules do we have? Well, we have two. One gives us the first part, one gives us the second part. Doesn't matter which one. Let's pick the left one. Okay, so the first and elimination rule gives us A or B. All right, we could also extract the second piece, but let's postpone that for the moment. Just let's wait for that. Okay, so now what else do I know? I know A or B because I have deduced that, so I can try to apply elimination rule for that. Now that makes sense because when I reasoned about this, I said, okay, we can't progress here, so let's distinguish the cases in A or B. So let's do that. Okay, so let's distinguish cases. Okay, so this is an OR elimination. And we have two cases. One case we introduce A. Let's label this X. Okay. And in the second case we introduce B. I don't know where I'm going to have to put this. Let me put it over here. Let's call this Y. Okay. And in each case I have to prove A or B and C. And in the second case where I have that assumption, I also have to prove A or B and C. Okay? Now, how do I prove that? Okay, can I make progress now from the bottom up? Yes, because I can prove A because I have the assumption A. So this just follows by OR introduction, right? By the first one because we have that. Okay, let's look at the second case. In the second case, I don't know A, of course, because that's only for this case. In the second case, I know B, and I know A, and I'm trying to prove A or B and C, okay? And I still know this conjunction because the conjunction is available in a hypothetical proof as often as I need. Okay, so those are the two things I know, this thing, and I know B. Okay, can I prove A now by itself? From this and B together, can I prove A? No, I still don't have enough information. And the informal proof, I said, well, we distinguish cases here. The next thing is we distinguish cases here. So I have to distinguish cases of A or C. How do I do that? Well, I have to use my assumption again. So I have A or B and A or C. And this time I use the second elimination rule to get A or C. And I do that so that I can apply the OR elimination rule again. Okay, so now I have the OR elimination rule again. I get two assumptions. The first assumption is, let's call it U. The second one is W. The assumption U is called A. U, okay? And I still have to prove, in this case, A or B and C. But we already know how that's going to go. So let's just write that down. In the second case, what's my new assumption? C, right? Because that's my assumption. Right? So that the one labeled W is going to be C. So let's write this here. Okay, so now I still have to prove, in this case, A or B and C. All right. Now can I proceed by an introduction rule from below? Do I know A? No. Do I know B and C? That should follow, right? So I can use here now, working upwards, the second introduction rule to prove B and C. And how do I conclude B and C? Can I work bottom up? Yes, it follows by end introduction. Okay. Okay, so magically I put B exactly in the right spot. Okay. So the whole trick of the game is to figure out where to put the assumptions. But when you're done, everything looks like a proof. Okay. Okay, so this is now hypothetical proof that with this assumption here, you can prove that. And we use the assumption twice, which is not too surprising because the assumption is a conjunction, and usually when we have a conjunction, we need both pieces. Okay? Questions on this? Proof makes sense? Okay, so the general strategy, to repeat it, is you always use introduction rules from below, elimination rules from the top. And you always have to make sure in your mind that whatever sub-goals you construct, you can actually prove. Because it's very easy to get into a situation where, well, you try to use the introduction rule to prove A, but you actually can't because you don't have enough assumptions to prove A. Right? And I think the trickiest part of this whole calculus is the OR elimination. Right? Because the OR elimination has this weird form where it says, distinguish two cases of between a disjunction when you're trying to prove something and then going to the two branches. And so that's where usually people had trouble to figure out how to apply the OR elimination. Okay? Everybody okay with this proof? Okay. Okay, so that was one. The other one was on the temporal logic. Okay, so I thought I would spend just like 1 minute on that. Okay, so the idea was to take the basic judgment of truth and relativize it to a time, right? And so basic judgment here is A true at time t. Okay. So the first thing is pretty straightforward. You take the rules that you already have, and you make them take place at time t, right? So for example, you might say something like, to prove that A implies B at time t, okay, you assume A at time t, call that x, and you have to prove B at time t, okay? And then the elimination rule has to be similar. If you know A implies B at time t and you know A at time t, then you get B at time t, and that's implication elimination. That's pretty straightforward. The question is, what is the definition, and therefore our verificationist point of view, what's the introduction rule for next A? So when can we conclude circle A at time t? And this would be the circle introduction rule. Okay, I think a number of you had this right, so somebody can tell me. Right, A has to be true at time t plus 1. Okay, that's about as simple as you can get, right? That's how I said. Circle A should be true at time t if A is true at time t plus 1, and we package this as an introduction rule. Now, the elimination rule has to say, if you know that circle A is true at time t, what can we deduce from that? A has to be true at time t plus 1. Okay? That's it. Okay, we have introduction elimination rules. Now we have to check they're sound and complete, right? Let's check if they're sound. Okay? So any way of introducing the circle and then eliminating again, do you gain information? No, because this premise is exactly the same as this conclusion, so you don't gain. So it's sound. Is it complete? What do you have to check? We have to take an arbitrary proof D that circle A is true at time t. And you have to apply the elimination rule in some way, shape, or form so that from the result you can reintroduce a connective. So how do you do that? You just apply this elimination to get that, and then you apply the introduction again to get it back. Right? So I don't have to write it down. Everybody can see it. So it's almost too easy, right? So I think the people were doubting themselves because it seemed too easy, but that's what it is. Okay? So temporal logic is very, very easy to define if you only have the next operator. Okay? Now nevertheless, this is an extremely rich thing, and we'll see a little bit later in the lectures what you actually get out of this in the end. But there's one question I wanted to pose to you as sort of a side remark. Let's get rid of the implication because that is straightforward. Okay, so we all believe this should be the case. Let's do it like this. All right, that's kind of uncontroversial. If tomorrow A and B is true, then tomorrow A has to be true and B has to be true, right? Okay, pretty simple. Now, what about this? Should that be true? Should circle distribute over disjunction? Maybe, maybe not, right? Okay, that's a good question. So here's the maybe not argument. Or maybe somebody else wants to tell me, somebody who said no, want to make the argument?
This means you could tell today which one is going to be tomorrow?
Yeah. So if somebody's going to flip a coin tomorrow and tell you A or B, can you tell right now at the current time whether he's going to give you heads or tails, right? Well, you can't right now, right? You have to wait till tomorrow. Is there an argument for why this should be true? Hmm? Yeah, we're in the intuitionistic case. But still, there might be an argument why it's true. Is anybody willing to make that? Yeah? We know it's going to be one or the other, right? He's going to flip a coin. Definitely, he's going to give us A or B. Well, just because we don't know right now, it's going to be one or the other. So as a constructivist, I don't buy that argument, okay? Okay? Because proof should be constructive, so proof of disjunction should tell us which of these two is true, right? And if I have to look into the future, that doesn't really tell me much, okay? So from a constructive point of view, this is questionable. So how do you actually write the rule so this thing is not really true, for example, that you can't actually prove that? And what are the consequences of that? So it's very easy to write the rules for conjunction and implication because nothing like that's going on. When you can be disjunction, it becomes a little bit tricky and one has to make that decision. And I've pondered over these kind of questions with similar systems quite a bit in the past. It looks trivial, it looks simple, but to get the right system and get a good computation interpretation is tricky. So one of the things we'll be able to do later is we'll give a computation interpretation of this logic. And then we can ask, well, according to its computation interpretation, should there be some kind of a proof which takes this and goes to there, which corresponds to some kind of a program, and how does a program compute? Does it look into the future, or does it not need to look into the future, or what's going on? Okay, so we can answer that question. So even in this very, very simple thing, okay, there is some interesting things hiding, okay? Okay, so those were 2 points of the homework assignment, and we'll see more proofs, so you'll see a little bit more of example how to actually construct them, okay? All right, so what I wanted to do now, I'll leave this up here, is talk about the propositions as type, or the so-called Curry-Howard isomorphism, okay? So at the beginning of the 20th century, there was a big argument in mathematics about, whether mathematics should be constructive or not, okay? And on the one side, there was Hilbert who said, no, not at all. I always do proofs by contradiction, that's perfectly okay. And then there was Brouwer who said, no, you get meaningless results if you're allowed to reason about contradiction, okay? And, the war raged for a while and Hilbert won. Okay, and Brouwer was pushed off to the side and basically said, well, mathematics doesn't have to be constructive. And what does it mean not to be constructive? Means that when you're supposed to prove a proposition exists of A of X, you can do that without ever exhibiting a particular term T for which A of T holds. So in mathematics, it's perfectly okay. You just show that it's impossible for such a T not to exist. Okay, I don't have to say what it is, but it's impossible for it not to exist, so therefore this should be true. And similarly, for A or B, which is our version of this, it's possible to prove A or B without proving either side. Okay? And the prototypical example of that is A or not A. Okay, now we haven't introduced negation, but in intuitionistic logic, usually negation is just defined as A implies falsehood. Okay? And so rather than defining by introduction elimination, which you can perfectly well do, they say, well, we already have a means to express it. We don't need separate introduction elimination rules, and it's just this thing here. And so this thing becomes A or A implies falsehood. Okay. Now I haven't shown you what falsehood is. I can do in a second, but the thing is that if you look at this and you're trying to prove it, you have no assumptions. You can only apply, if you follow my strategy, introduction rules from below. So you'd have to proceed by either proving A by itself or proving A implies falsehood by itself. Neither of these is obviously possible because we don't know what A is. So we don't know if it should be true or contradictory. And therefore we can't prove that if you believe my assertion that the strategy I gave you is complete. Okay? At the end of tomorrow's lecture, we'll be able to show that you cannot prove this in general. Okay? For now, you have to believe me, we cannot prove this, okay? But in classical logic, you're very easy in assuming that, well, everything is either true or false. So therefore, A or not A should always hold. If you fail to be able to prove A, then it's okay to assume A and try to derive a contradiction, okay? So, right. So then, I guess Brouwer's program got a sort of renewed boost in the 80s with this realization that constructive mathematics is essentially doing computer science. And computer science became interesting as a field. Okay? And so now, computer science has vindicated Brouwer. Okay? And in the full generality, the existential quantifier and the disjunction and all of that, you'll see that in Bob's lectures in type theory. So I only give you like sort of a faint image on that by looking at only the propositional part. I leave the quantifiers and so on to Bob, but even on that, you see that there's a distinction between classical and intuitionistic logic because you can use the law of excluded middle, but you can't use it in intuitionistic logic. Okay? All right, and so now we want to reap the benefits of that, and we want to see in what sense the constructions that we make in natural deduction actually correspond to programs. Okay? So that's what Howard discovered in '69. Okay? If somebody reminds me, I'll tell you what Curry did in '35, a little bit later. '35 seemed to be a very important year because that's also the year that Gensen wrote his paper on natural deduction and the sequent calculus. So a lot of very, very important results came out. Okay. All right, so let's start with conjunction. Okay. So, okay, let's start with the introduction rule. Actually, let's see where I'm going to do this. Okay, let me do it over here. I'm going to, okay. So we have A true and B true, then A and B is true. Okay? So I omitted the true, so I have room to write what I actually want to write here. This is the end introduction rule. Okay, so if I want to record the structure of the proof of a conjunction, if I want to record the structure of the proof, you can see, if that's our definition, then a proof of conjunction should be a pair of two proofs. Okay, one proof of A and one proof of B. That's all what this rule tells us. Does that make sense? That's all I have, okay? So I'm going to write this. I write M colon A and N colon B, and I write the pair MN is going to be a proof of A and B, okay? So my basic judgment is now M colon A, and it means that M is a proof of A, or a proof term of A. Okay, so I'm going to go back and forth between saying a term of type A or a proof of A, okay? Because I'm generally going back and forth between these 2 points of view, and I'll put them here, and we'll fill that in. Okay, so here we have our propositions, and here we have our types. So the proposition A and B as a type corresponds to a product. So it's going to be something like A cross B, right? Because it's inhabited by pairs. Okay, that's what a product type is. Okay. All right. So then what do the elimination rules correspond to? So elimination rule says from A and B we can deduce A. Okay, so that's and elimination 1. And also it says from A and B, by the second and elimination rule, we can get B. Okay, so now let's say we have an arbitrary M of type A and B. So what would be the proof of A in that case? Right. So we often write this as a first projection of M. Okay. Now, it would have been wrong to write this rule just as a side remark, to say if M comma N is a proof of A and B, then M is a proof of A. Okay. And the reason this would be wrong is because not all proofs of A and B have the shape of a pair. And so we can't always apply that rule, but we always want to be able to apply that rule when we have a proof of A and B. Okay. How could this rule fail to apply? Right. If A and B is an assumption that I have, it's labeled, okay, by some kind of a variable. I don't have an actual proof of it. I just say, assuming I have a proof of A and B. And then I couldn't apply this rule, and that would be bad because I wouldn't be able to get the component of the pair out. So we can't write it like this. We always have to write the judgment we applying the elimination rule in its most general form. Okay? So we can always apply the elimination rule. Otherwise, the system would become incomplete, and that would be not good. Okay, so not like that, but this way. And then here, if M is a proof of A and B, then the second component of M is going to be a proof of B. Okay, so now let's think about the local reductions, or what they correspond to. So if you want to check the soundness, we check that every introduction followed by every elimination actually can be reduced. Okay, so this is an introduction followed by this elimination. So the proof term of that would be, this would indeed be a pair in that particular case. So we would get pi 1 of the pair Mn. Okay, and that would be a proof of A. Okay, if M is a proof of A, N is a proof of B, the pair is a proof of A and B, taking the first projection gives us a proof of A. Okay, now what does a reduction do? Okay, now you have to remember back. What does our local reduction do in this case? We use that proof of A, right, which we called M here. So the local reduction says this reduces to M. Okay, so usually we don't write the types in, I just did to clarify. So the reduction is taking the first projection of the pair Mn, reduces to M. Okay, our second local reduction says taking the second projection of the pair Mn, we reduce to N. Okay? Okay, so I'm just writing down on the proof terms what I just did yesterday. Okay, hopefully people can remember it well enough. Okay, questions on this? Make sense? So the local reduction we use to witness the soundness of the rules is actually a rule of computation taking the first or second component of a pair. Okay. Okay, what was our local expansion? That's a little bit harder to remember, so let's write it here. So if you have a proof D of A and B, okay, anybody remember how this works? If we expand it into, somebody can tell me?
The pair consisting of the first projection and the second projection.
Right. So we take this proof of A and B, and we apply the first elimination to get A, and then we use it again to apply the second elimination to get B, and then we reintroduce A and B. Okay? So that was the witness for the local completeness. We can apply the elimination rules in such a way that we can reintroduce a conjunction. Now, if this is going to be some arbitrary M, we're using it twice. We're using it here and we're using it there. Okay? And then this A is going to be the first projection of M. And this is going to be the second projection on M. And then this is going to be the pair consisting of the first projection of M together with the second projection of M. Okay? So if I write it down here, I would write something. If I have an M which is of type A and B, then I can expand it into the pair consisting of the first component of M and the second component of M. Okay. So when we look at the operational semantics of a programming language that's based on these constructs, we'll see that these are actually computation rules because they actually reduce the term into smaller ones. This one is sort of an equality which says that any term of type A and B is actually equal according to its type to some expansion of the components. Okay. So we don't compute with that rule, but we compute with these two rules. Okay, everybody still on board with all of that? Okay, so let's go through more constructs and see what happens. Okay, so implication is the next one, natural one to look at. Okay, so the introduction rule for A implies B says we introduce a new assumption, call it X. Then we have some proof here, which gives us B. Okay, and X is available only here. That's the scope of X. All right, so when we try to assign terms to that, we say, well, there's going to be some term m, which is the proof of b. We don't know what that is. What is our proof of a? What's our proof of a? There is none, because we just make an assumption. What would be a natural way to label it? X, because we already used that x. So while we're reasoning here, we say, okay, we have some proof of A. We're just assuming it exists, but it's not really a closed term. So we don't really know what it is because it's just an assumption. So label that with a variable. Okay. And then the term here is going to be, okay, it's going to be lambda x m. Okay. So this is a function which, if you give it a proof of A, it gives you a proof of B. So that's a way to think about it, right? And you should only be able to apply it to proofs of A, and it will guarantee to get back a proof of B. That's why we have a lambda abstraction. And the fact that this is a lambda abstraction, okay, was the essence of Howard's paper in 1969. That's the thing that he noticed, okay, that we can look at the structure of natural deductions. We can assign proof terms to them. And if you assign proof term the right way, oh, this is a lambda abstraction. The proof terms just constitute a lambda calculus. Okay. Moreover, computing with that lambda calculus corresponds to the proof reductions that we know about from before. Okay, we need to look at the elimination rule. So in its most general form, if you have an M which is a proof of A implies B, and N is a proof of A. Okay, how do we get a proof of B? Okay, substitution. Okay, that's looking ahead one step farther. Application. It's applying M applied to N. And that's going to be proof of B. Okay, so usually in functional program we write application by juxtaposition. So we say M is applied to N, and that's our proof of B. Okay. All right, so now we'll come back to the other remark. So if we introduce that and then eliminate it, what does it actually look like? Okay, so let's actually write it down, because we go from x colon b to m, x colon a to m colon b. And then we have lambda x dot m, which is A implies B. And then here we have an n of type A, and then we apply implication elimination, and we get lambda x dot m applied to n. That's going to be our proof of B. And now our local reduction, okay, whoops, I should justify this also like that. Okay, our local reduction says we take this proof here, okay, and we substitute for all assumptions over here. Okay, that's what our local reduction said before. So maybe I should even write the names of this in so we can remember what that was. So there's going to be some proof D here, and there's going to be some proof E here. And here we're going to have, okay, don't write in the proof terms yet. We have B, then we have D, which depends on X, which depends on A, labeled X, and we substitute E in here. So that was our previous reduction, okay? So let's put in terms, okay? So here we had previously X colon A. What would we plug in here for X colon A? What's our proof of A that we now have? N, right? The proof E is up here, and the proof term is N, right? Because that's what E actually proves. So instead of X colon A, we have N colon A. Now instead of the proof D, what kind of a proof do we have? It's not D exactly. Right, it has to be D. Throughout D, there's going to be uses of X, and we have to substitute N for every use of X. So it's going to be N substituted for X and D. And what proof term does that give us at the bottom? It doesn't give us exactly M. It gives us N substituted for X, right, in M. Okay? And that's because the term M will also contain occurrences of X, because that's what you use throughout here. Okay? Okay, so that's what we get. So we get N for X and M colon B. So if I summarize that, the local reduction is if I have lambda x m and I apply it to n, then by local reduction I get n for x in m. Okay, which is usually called the beta rule. Yep? Okay, so a proof is like a figure, right? Like a two-dimensional figure. And a proof term is something that I write down here, which is either a pair, projection, a lambda abstraction, or application. Okay, so a proof term is a notation from which we should be able to reconstruct the two-dimensional derivation. Yeah? Yeah. That's right. Okay. Other questions on this? Yeah.
Since x is a whole in m and is a whole in d,
Yeah.
is x sort of standing for both the first and the first term?
Yes. So if I were more precise on this, I would give these two different names. But this is the only time we have to distinguish them, so I took a shortcut. Yeah.
And then would it also sort of make sense with the d with n substituted for x, then you might use the e substituted for x?
Right, except the substitution of e for x is denoted by this part here, because d is some kind of two-dimensional thing with x somewhere at the top. And this notation, putting e above the line, means to plug in e for x in d. Okay. Okay. More questions? These are all good questions. Okay, let's look at the local expansion. What that means. So we have to remind ourselves what it is. So we have an arbitrary proof of A implies B. Okay, so it's hard to pronounce, I'll just write it down. So we're trying to find a proof of A implies B, which proceeds by implication introduction, introducing x. Which proves B and introduces x. And I prove that from D by implication elimination. Okay? So I can apply the elimination to what I know in order to reintroduce the implication. So that's witnessing the completeness, and that was our local expansion. So let's just write in what we have. Is this is a proof term for A implies B, and this is a proof term for A implies B. What's the proof term for A? X, right? Because it was just an assumption. All right. What's the proof for B? It's an application of M applied to X as the proof of B. And what's the proof of A implies B now? It's lambda X, M applied to X. Okay? So at this point, it becomes a little bit clear that there is some condition on this expansion that we didn't make very clear before, which is that this only makes sense if you choose an X here which doesn't occur in the rest of the proof. Right? So this X, you have to make sure that it doesn't conflict with any other assumption that's being carried out here. Okay, so that this X doesn't occur in M. Because otherwise you would create confusion, because this X of type A being here would have this local scope and anything that might exist in M. Okay, so the local expansion is going to be this. So it's going to be, say, if I have an M which is of type A implies B, I can expand it into lambda X M applied to X with the condition that X is not in M. Okay? So now we can compare these two. You know, we often think of this rule. So this is called beta usually, and this is called eta when you write them as equalities. We can think about why these two should be equal if we think, well, extensionally. So applying this to an arbitrary argument, okay, gives us M applied to N. If we apply this to an arbitrary argument. If we apply this to an arbitrary argument, we get lambda X, M applied to X, and then applied to N, right? Okay. Now what happens with that? Now this beta reduces to, well, we have to substitute n for x in m applied to x, but that's just equal to m applied to n. So if you apply m to an arbitrary argument, or if you apply lambda x, m of x to an arbitrary argument, you get the same result, okay? And therefore, those two functions should be considered equal, because whenever you apply them, you get the same answer, okay? So that's a justification. And similarly for pairs, I think, if you take a pair m, a with b, you take the first projection, you get pi 1 of m. If you take the first projection of this pair, you get also pi 1 of m. And if you take a second projection of m here, and you take the second projection here, you get also pi 2 of m. So if you observe a pair by taking the projections, you get the same answer on both sides, and therefore the two pairs should be considered equal. Okay? Everybody okay with that? So these eta rules embody a form of extensionality. Okay? Okay. Any questions on what we have so far? Okay, so let's complete our table here. So A implies B correspond to a function. And if you think about it as proofs, we think about it as a function from proofs of A to proofs of B. Okay, so it's a function on proofs. Okay? And the way the function computes is the way we're used to. The function computes by substitution. Okay? Somewhere else I should put a more general correspondence. Okay, so we have that correspondence that propositions in logic correspond to types. Okay? Now, what does a proof in logic correspond to? Okay. It corresponds in this particular case to a lambda term, right? So a proof corresponds to a term that you're computing with. Let's see, what does an introduction rule correspond to? What does an introduction rule correspond to? A constructor, right? Because you construct, for example, a pair. So an introduction rule corresponds to a constructor. Or here you construct a function, okay, out of the pieces. So an intro rule is a constructor. An elimination rule, what does an elimination rule correspond to? Well, as a term formation thing, what does it do? It leads to evaluation, but what does it do as a term formation? An accessor, or I'm going to call it a destructor. Right? Because it destructs a pair into the components, or it takes a function and destructs it into the body, okay, and substitutes for the argument. So the intros are constructors, the elimination were destructors for types. Okay, what does a reduction, a local reduction correspond to? A step of computation, right? A computation step. Because we do a local reduction, and then we see, okay, it's a step of computation. And an expansion corresponds to some equality, extensionality, some equality. Okay? Now, it turns out that there is a number of, so basically we have a fairly good explanation of a lot of things that are computational. We know what types are, we know what the terms are, we have constructors and destructors, we have computation steps, and we even have a way for reasoning about equality. There's some things that proof theory, at least as we've done it so far, it doesn't give us an unambiguous answer. For example, you can't answer with what we have here on the board the question whether a functional language should be called by value or called by name. Okay? The proof theory doesn't tell you that. Okay? So proof theory doesn't tell you everything, or you might have to go through a lot more trouble to figure out the answer to that. Right? To figure out, well, maybe our proof theory is too simplistic and we need to do more in order to find the answer to those questions. Okay? But it tells us a lot. So if you want to design a programming language and you want to know what should be my types, how should I introduce and eliminate it, and how should I compute, you can look at this table and you get a lot of information. The one thing that you don't get is sort of an evaluation strategy. You have to think about that separately. Okay? Does that make sense? Yep. Yeah. Okay, so let me think if I want to do this now. Okay. Okay, I'll do it now. Okay, this is part of your homework assignment. Okay, so I'm going to do a couple of proofs, and I'm going to do proof terms for those. And then I'm going to use equality to reason about those proof terms. Okay? Actually, let me give myself more room here. Okay, so the first thing I want to do is I want to reason about this. A implies B implies C, proves A and B implies C. Anybody know what that's usually called in a functional language? It's currying or uncurrying, right? So usually, I guess you would say uncurrying, right? Because this is the curried form where you don't use conjunction. Okay, so let's do the proof of that. The question is, do I have to write the proof figure? Maybe I should do it just once, okay? And then we assign the terms. Okay, so what we do is, we start up here with an assumption. Let's call it F. A implies B implies C. And I'm trying to prove down here that A and B implies C. And hopefully if I play my cards right, we should be able to prove that. Okay, do a reason. So there's going to be some proof term which I eventually fill in. Do we reason downwards here or upwards? Downwards with elimination or upwards with introduction? Upwards. Okay, so implication introduction, I introduce X. Actually, let me call it for my own reasons. Let me call it P. Okay, and so now I have an assumption P of A and B. And now I have to find some proof of C. All right? So now what do? Do I reason upwards? Well, I can't. There's nothing to destruct anymore, right? No introduction rule applies. So I have to reason downwards. Do I reason from F or do I reason from P? P, okay. Say it again. P is an assumption which we introduced right here. So this is justified if I reuse the same letter, right? Because we use that implication introduction. Good. So we can reason downwards by elimination rules. And we extract the first piece. Let's call it pi 1 of P. Would be a proof of A because this is the first elimination rule. Everybody with me so far? Okay, so now what do we do? Now we can implication elimination here. And so we get a proof of B implies C. Okay. And what's the proof term for that? F applied to pi 1 of P. Okay, everybody on board here? Because we apply an elimination rule when this and A, and we get B implies C. Okay, how do we proceed from then on? So now the gap to fill is we have to go from B implies C down to C. Right? How do we do that? We want to be able to get B, right? How do we get B? Yeah, we reuse P again. So P colon A and B. And we apply the second elimination rule, pi 2 of P, to get B. And then, so this is and elimination 2, and this was justified by P. And this is implication elimination. So the proof term for C here is then going to be what? It's going to be this thing applied to this thing here. So it's going to be f of pi 1 of p, and that whole thing applied to pi 2 of p. Okay, everybody okay with this? Okay. So if I want to be quick about it, I would say if f has this type, then f of, no. Oh, I forgot the last step. The last step says this is lambda p, f of pi 1 of p, pi 2 of p is a proof of that, right? Because there we introduce the p, so this becomes a lambda. I would say lambda p, f applied to pi 1 of p, and this whole thing applied to pi 2 of p is a proof of a and b implies c. Okay? So you can see this notation here is actually a little bit nicer than this in some ways, right? Because I can write it in one line, and if I just give you this information here, you can reconstruct this two-dimensional form, right? Because I tell you at each point what to apply. This is implication introduction. This is implication elimination, another implication elimination, first and elimination, second and elimination, right? So all the rules and the way you apply them is contained in the proof term. So it's a bijection, right? Which is why it's called a Curry-Howard isomorphism. So you can take a proof, okay, this two-dimensional structure, and you can extract the proof term just by annotating each line with the term. And if I give you a term, you can reconstruct as two-dimensional proof because it has all the information in it. Make sense? Okay. So let's do the other direction. And maybe we can do it quicker. I don't know. If I have G, which is a proof of A and B, implies C, and I try to get some proof of A implies that B implies C. Maybe you can just do it in line. Maybe we can do proving here by programming, right? So it goes both ways. You can write programs by writing proofs and then extracting the program. Or if you want a proof, you can also write a program and then essentially type check it, right? So what is this program here? Any thoughts? Yeah?
Lambda x dot lambda y.
Yeah, it was, oh, okay. Okay, so lambda x, and x will have type A, right? I'll write it like that. Then lambda y, and y will have type B, right? So that corresponds to two implication introductions. Now, the gap we have to fill here has to be some kind of a term of type C, right? Or a proof of C, if you will, okay? How do we get a proof of C? So you said it quickly, so we don't have much to work with. We have G, okay? So we take G. We have to apply this to a proof of A and B, which is going to be a pair. And the pair is going to be, well, the pair of X and Y. Okay, so you can see there's some advantages to writing proof this way, right? Okay, any thoughts on that? Are we doing okay here? All right, so now, okay, so this is a slight excursion, but it's interesting because it tells you reasoning about functional programs. Okay, so we say that two types are isomorphic. And the types I'm talking about in this example is this type here and this type here. Okay, if there's a pair of functions, one goes from this type to this one, and the other one goes back from this one to the first one. So that's that you compose them both ways, you get the identity. Then we say the types are isomorphic. Okay, Ed might have more to say about that. Okay, but this is the way it turns out here in natural deduction. Okay, so I claim that these two types are actually isomorphic. Okay, so they have the same information contents. Okay, so let's try to check that. Okay, so how would we check this? Okay, so what I want to do is I want to go from F back to this, for example. Okay, so how would I get a term for this? Okay, so I want to check if F is equal to, okay, if I go around and compose these two functions, okay, what would be the composition of those two functions? So we get it by substituting this thing here, which is a proof of A and B implies C, okay, for this assumption in this proof. And we get another proof of A implies B implies C. Okay? Does it make sense? We do it by substitution because the meaning of hypothetical judgment is substitution. Okay. So what does a substitution do? Okay, so this proof here is going to be lambda x, lambda y. Then for G, I substitute this term, lambda p f of pi 1 of p, and that applied to pi 2 of p. Okay, this whole thing, this lambda p, applied to the pair x, y. Okay, and that should be, if I did this right, should be of this type. Okay, I don't care about this particularly, but it should be of that type. You can see what I'm doing here. I'm substituting this proof of this for G in this proof, and I get another proof where I just plugged in this for G. Now am I doing my substitution? Okay, doing okay so? Okay. So now how can I reason about this term? What can I do with this term if I want to prove it's equal to f? We can reduce, okay? Where can I reduce? Let's look. Here we have an application to some arguments. So I can plug in this pair for p. So I get lambda x, lambda y. Then I get f applied to pi 1 of the pair xy. And this whole thing applied to pi 2 of the pair xy. Okay? Did I do this right? Okay, good. So now what can I do here? Can I reduce this? Can I reason by extensionality? What can I do here? It can be reduced because I have pi 1 of a pair, right? Okay, so this reduces to lambda x, lambda y, f of, x, is that right? X. And then here the second projection, let me do it in one step. What does that second projection of the pair x, y? Y. So f of x applied to y. Okay? Okay, can I do anything here? I can't reduce anymore, right? There's no redux. It's not a function applied to an argument or projection, but I can do something else. Eta expansion. Okay, so let's start here with f. What does f expand to? Okay, so f has this type, so it should expand to lambda x, f applied to x, right? And what's the type of f applied to x? B implies C, so I can apply eta expansion again, right? And so this expands again into lambda x, and then lambda y, f applied to x, and that applied to y, right? Again, by expanding f applied to x this time. Okay? Do you notice something about the two lines? Those two things happen to be equal. Okay? So by expanding f and reducing this composition, I've shown that if I take f and then I compose it with g, by substituting it into here, I actually get two things that are equal. Okay, if I compose them in one direction, they're equal. Now, part of your homework assignment will be homework, check the other direction. Okay? And if all works out, then we know that these two types are actually isomorphic. Okay? Second part of the homework is the following. One thing I assigned last time was this weird law that said A implies B implies C, okay, is equivalent to A implies B implies that A implies C. Okay? And I asked you to check if this is true or not. Okay, did anybody find out? Are they equivalent or not? Anybody got that far?
Yeah, they're equivalent in both directions.
Okay, so they're equivalent. You can prove this thing in both directions. So there's a distributivity law of implication over implication. Okay, maybe somewhat surprising, but yes, there it is. Okay, so is this an isomorphism? Okay, so in order to do that, what you're going to have to do is you're going to have to prove it in both directions, just the way I did there. Write down the proof terms, okay, that correspond to programs, and then compose them in both directions, make sure or check if they actually compose to the identity or not. Okay? Assignment clear? Okay, good. So that'll give you some exercise in writing out proof terms for these things, and also manipulating them using beta reduction and eta expansion as means for computing. Okay? Okay, any questions on this? Okay, so let's complete our program. So the completion of our program would be to fill in more of this table. Okay, so I'm going to fill in more of this table. I'm going to do disjunction next. And then I'm going to fill the gap from last time when I didn't introduce falsehood. Okay, some people have asked me about that. Okay, so, yep.
If this isn't an isomorphism, would we have to say that?
No. You would just get to two things that are patently not equal, but you have no way of proving that they're not equal. Yeah. So just like when I asked you to prove whether two things are equivalent in both directions, when they're not equivalent, you have no means of proving that they're not equivalent right now. Okay. Yeah. So you'll just observe, hey, these look different. Okay. Okay. Yeah, so this is something that also came up in a number of questions. These tests on introduction elimination, right? The local soundness and completeness, right? There is some level of informality to them, right? But to make it really precise, that one of two things happens. Usually, if you try to make it fully formal, then what happens, the next example you think about doesn't fit quite the same framework, and then you have to change the definition, okay? Or you get kind of in the realm that I wanted to avoid, where you assume all of mathematics in order to introduce mathematics, right? Which is also not a good strategy. But we're doing something else. So in the next lecture, we'll actually do that. We put ourselves onto a step above the logical system, and we reason about that logical system. And when we're doing that, I'm not worried about the question of, well, is it okay from a Fontatian perspective to do that? I'm just going to do it, okay? And so if you want mathematical precision, that'll be in the next lecture, okay? And what we're going to prove there is the global version of these local soundness and completeness theorems that we had so far. Okay. So I won't be able to, of course, do the real full proof of everything, but I'll give you a sketch of how all that works. Okay. But now we still have to complete the operational interpretation. So the question is, what corresponds to A or B? Okay. So I'm going to try to do a little more quickly. So we have A or B from A, and A, from B we get A or B. The first and second or introduction rule. Okay, so if you have an M of type A, then, or an M of type B here, okay, the thing what we do is we just tag the term and tell us whether it came from the first or second, and usually these are written as injection on the left or injection on the right of M. Okay? So if we have a proof of A or B, we can tell whether it came from the first or the second, okay, a rule, because it's going to be in left of M or it's going to be in right of M. Okay, so that's how we tell. So rather than a pair, we have these two different sort of injections into that. And then the OR elimination looks like this. So if we know A or B, we assume A, label it X, we have to prove C. We assume B, label it Y, prove C, or elimination, which introduces X and Y. And at the bottom, we've got a proof of C. Okay. So now this has to be in full generality, so we don't know what proof M of A or B looks like. But we know what to label that. That's going to be X, and this is going to be Y by some slight abuse of notation. And then this is going to be some N, which is a proof of C, and N may contain X. And this is going to be some proof P, which is a proof of C, and P may contain Y. And what is my overall proof of C? Okay, the proof of C is going to be a case construct. It's be a case. I'm going to write it like this. So we did case over M, depending on what N is. If M is an in left, okay, then we go this branch. So we do X and then N. And here we have Y and then P. And the second case accounts for the fact that it was an in right. Okay, so this here is to say this is N, which may contain occurrences of X, but we delineate the scope. So the scope of X is just N, and the scope of Y is just P. Okay. All right, and then the reductions will be something like this. If we take a case, and we have an in left of M, and then X dot N and Y dot P. Okay, so what does it reduce to? So we know it's an in left. What's the type of?
N with M substituted for X.
Right. So we know M is of type A, right? And we know it's an in left, so we have to pick the first branch. And M is of type A, so we can substitute it for X because we assume that X has type A. So this is going to be M substituted for X in N. And the second one is if we take a case and it's an injection to the right of M, X dot N, Y dot P, then it reduces to, okay, M, but now substituted for Y in P. And that's okay because if it's in right, we know it has type B. So we can substitute it for Y, which was assumed to have type B, in P, and get something which has type C. So the overall type of this whole case will be type C, and the type of the right-hand side is also going to be type C. Okay, so it works out. Now, I don't think we talked about the local expansion last time. Okay, if I have an arbitrary M of type A or, well, okay, let me write it down first that way. If I have A or B, an arbitrary proof D, how do I expand that into something that applies elimination, then reintroduces the disjunction from the pieces? Right, it has to become a case. And in one case, I'm allowed to assume A, call that X. In another case, I assume B, call that Y. Okay, so now if I have that rule here, the or actually, with this or rule, I can pick the C. Which C do I want to pick? I want A or B because that's what I want to conclude at the end. So I want to pick A or B, and then this is the second introduction, and this is the first introduction. Okay, so that's the expansion. Okay, make sense? So it's actually, we break down the or by an elimination rule, and then we apply the introduction rules separately in the two separate branches. So if I write this down here, if M is an arbitrary term of type A or B, I can expand this into, okay, a case of M. If it's the in left, then I reconstruct the in left. If it's an in right, then I reconstruct the in right. Okay, so that's the local expansion. And that's just putting proof terms into the figure that I wrote over there. Okay, and so an arbitrary term should be equal to this. Okay, if I reason extensionally. Okay, so the reason I actually did this is because I owe you from last time. Hopefully everybody's written this down. The definition of falsehood. Okay, and this is sometimes interesting because it corresponds to, because it's usually used to define negation, and negation is interesting because it distinguishes classical and intuitionistic logic. Okay, so when is falsehood true? I stacked the deck here in my favor. Okay, never. What does it mean it's never true? What it means there is no introduction rule. We couldn't possibly introduce a proof of falsehood, right? Because there isn't one. There isn't supposed to be one. So there's no introduction rule. All right, so that was easy. Now what should be the elimination rule? Okay, so now this is tricky. So let's think of it this way. We know the following should hold. A or falsehood should be equivalent to, okay, A. And in fact, they should be isomorphic, okay? So it should be sort of the unit of disjunction. When you take a disjunction with falsehood, either A is true or false. Well, false could never be true, so it has to be A, right? So that's what this basically says. So you can think of falsehood as being a disjunction with 0 branches, 0 possibility, where the ordinary disjunction has 2, right? Does that make sense? It's like a disjunction, but no alternatives, 0 alternatives. If you think about it from that point of view, okay, what should the elimination be? So here we say, if we have A or B, we distinguish the 2 cases, we prove C in both cases, then we conclude C. If we have falsehood here, there's 0 alternatives, so we don't need to consider any branches. We're just outright allowed to conclude C. Okay, so the elimination rule says, if I know bottom is false, then, oops, not false. Bottom is true, then indeed everything should be true. This would be the bottom elimination, okay? But we still have our tests to apply. Is this sound? Okay? So any introduction for bottom followed by any elimination, can we reduce that? Yes, because there's 0 cases to check. Very, very easy. Okay. So it's sound. We didn't make any mistake there. Is it complete? So the question is, can I take an arbitrary proof of bottom? And can I expand it into something where I can apply the elimination rule so that from the pieces I can reassemble a proof of bottom? Right. So this is a weird thing now. But the way I'm doing it is I'm applying the bottom elimination rule, but I pick C to be equal to bottom. Okay? That's the same thing I'm doing here. Okay? But let's think of a disjunction with no components. So then in this proof here, there's no branches, so we go directly from bottom to bottom. So it's just a 0 area analog of what I did here. So I can take any proof and I can convert it into one like that. Okay? So I actually introduce bottom here, just introduce it 0 times. Okay? Because there aren't any introduction rule, that's the best I can do. Okay, so this rule is strong enough. In fact, you can hardly think of a stronger rule than that. Okay? And it's also sound, so it's not too strong because we have to check it with no introduction rule. So that's what the rules give you if you apply the techniques to do falsehood. Okay? And let's see. Oh, top. I wanted to do top. Okay? Okay. Let's complete our table here before I do top. So what does A or B correspond to? Well, you may not have seen that, but usually it's called the sum type. Okay, A plus B. And the elements of the sum type are injections on the left or injections on the right, and you discriminate them by case. And what does falsehood correspond to? It's the empty type, right? A type with no values, okay? And so we can write that as 0, okay? And it's a unit of sum, right? Because A plus 0 is isomorphic to just A. So bottom corresponds to the empty type. Okay, so let's complete the picture here. And let's think about top. Okay, when am I allowed to conclude that top is true? Where top means, well, truth. When is truth true? Always. Okay, so I don't need any premises here. I just say, all right, my introduction rule says top is true. Okay, good. Now, what would be my elimination rule or rules for top? How much information do I cram into the proof of top? None, right? Because there's no premises. So think of it as a zero-area conjunction because we have A and top should be isomorphic to just A, right? And so for conjunction, we have two elimination rules to get the two pieces out. And so we have no top elimination rules, right? Because we don't put any information in, we don't get any information out. Make sense? Well, is that sound? Okay. Any possible introduction followed by any possible elimination, can we reduce that? Well, yes, because there's 0 cases to check, so it's sound. Okay, good. Okay, is it complete? It means an arbitrary proof that top is true. Can we expand that into a proof that decomposes that into its pieces and then reintroduces top?
Use a new top introduction.
Yep, we just do, okay, we can. We extract the 0 pieces that we need, and then we introduce it out of all those 0 pieces, okay? So it's complete. Okay, what that means, this is actually interesting from the point of view of proof terms, is that if I have an arbitrary proof M that top is true, okay, then it should be equal to the proof that comes from top is true, and I'm using this notation here to saying it's sort of like a product except with 0 component. And so what this means is that any M of type top is equivalent to the unit element, okay? So what this means is that this is a type with exactly one member, which is just the unit element. Everything else is equal to it extensionally, okay? Okay, so if I want to write that down here, I have, if M has type top, then it expands into the unit element. Okay, and I didn't introduce the proof term for bottom, but I should probably do that. Okay, so if M is a proof of contradiction, then we usually write this as abort of M, being a proof of C. Okay, now there's no computation rule for that because you can't ever use that. But if you have an M of type bottom, then it expands into abort of M, which also has type bottom. Okay, so that's our expansion. So these two things are equivalent, and these two things are equivalent. Okay? Makes sense? Okay, so the homework I wanted was that checking that that isomorphism, if it indeed holds, by writing down the proof term and then composing in both directions and reasoning with them. And I also want you to think about the conundrum we had with the next operator. Okay, so what I want you to do is I want to assign proof terms in your temporal logic, okay, to the two rules, the introduction and the elimination rules that we had. Okay, and I want you to write down the reductions and the extensionality as rewrite rules on those proof terms. Okay, and then I want you to think about whether you can think of an operational semantics for that. Is there a programming language hiding there? What does it mean? Okay, and while you do that, you might also think about this question of, can I look into the futures, or what happens with the OR elimination? Okay, so that's the second part of the homework for this afternoon. Okay, so to come back now, what I did today, I established a very strong correspondence here between propositions and types. Propositions in intuitionistic propositional logic. So conjunction corresponds to products, implication to functions, disjunctions to sums, bottom to the empty type, and top to the unit type. Okay, and we have that proofs corresponds to lambda terms. The introduction rules are constructors for elements of the type, and the elimination rules destructors. Reduction are steps of computation, and the expansions correspond to extensional equality between computations. So just by doing logic, okay, you can actually derive the laws of a function programming language up to a point. What you don't get for free, as far as I know, at least from what I've shown you so far, is a question of sort of the strategy that's behind the operation semantics. Should it be by value? Should it be by name? Those kind of questions, you need other considerations to answer those. Okay. Questions? More points of discussion? Yeah?
With this summation type, so the type is in programming language is kind of like exclusive or, whereas the proposition is more inclusive, right? You can have A and B at the same time.
Yeah, it's a disjoint sum, right? A plus A is different from A because you have two copies, yeah. Yeah, so the usual type of Booleans, for example, if you want to find, would be, so bool, which has two elements, would be 1 plus 1, right? So it would be in left of the unit element or in right of the unit element, and those are the only members of that type. Okay. So usually in a functional language, you have some kind of a data type construct. Okay, so in ML, you might be able to say data type, okay, I don't remember the syntax, alpha, beta, sum equals in left of alpha or in right of beta. And so then that should correspond to, well, alpha plus beta, right? So that should, the sum type should be the constructors for element of that type.
Is there a joint type, like joint or? So this one's like exclusive.
Okay, so if you're asking for really an OR type, no, I think you just have disjoint sum. So there's other things one can do in order to take ORs and ANDs, but that's a completely separate thing that I don't want to get into. That's not directly motivated by Curry-Howard. So I have this one, which is disjoint sum, which can be defined like that. That's what you get. Okay, so what you have to spend a lot of time and effort to do is you want to construct recursive types, right? Inductive or co-inductive types and all that stuff, right? Like natural numbers and so on. Then you need to go to Bob's lecture, okay? So I'm not going to do that for you here. We're just looking at the purely logical part of that abstracts away from any particular data. We're not looking at Helen and whether she is mortal. We're just looking at A, B, X's, and so on. But with what we have, we can already construct a lot of the stuff that you need to write programs. Not everything, but a lot of the stuff. Yep?
Is it fair to think of the arrow type, A arrow B, as an exponential? Or is that the same sort of thing? Or
Yes.
Okay.
I think Ed will confirm that. If he nods, yes. Yes, it's an exponential. Yeah.
Exponential looks really nice, this type.
Yeah. Yeah, they do. It all, the triangle really does hang together. Yeah, so it really is an exponential. And the things which you get here as reductions, all these things just become equations, but they're stated in a variable-free form. Okay, so it's a little bit slightly trickier. Okay. Yeah?
Sorry, I'm really confused about this thing in bracket x9. I mean, I get the intuition, but is this like a small sentence in a series of sentences?
You mean this thing?
Yeah.
It's, okay, so what I didn't do here is I did not formally define, for example, the substitution operation. I just appealed you to into your intuition. So I could spend a whole lecture to talk about how to define substitution properly. I could probably spend a whole semester's worth of, okay? Because when you actually want to formalize this in a proof assistant or something, you have to be very, very precise about these things, and there's many different options. So here I just rely on your intuition to just substitute n for x. And here I'm relying on your intuition that x does not occur free in M, and I could define what it means for a variable to be free in a term, and how you can rename it to make the condition to come true, and so on. But I don't want to go to that level of detail because I don't think it really pays off unless I have you captive for a whole semester or, okay. Yeah.
I know it seems like a poor elimination rule, but is there anything you can compare the bottom, or you can learn bottom from bottom? Because that still fits in, a always thought this is spirit of eliminating bottoms, but,
No, actually, we're saying that, right?
well, yes, but our rule says that you can learn anything, but I'm saying you can learn, you could have a weaker bottom elimination rule, saying that bottom gives you bottom.
Uh-huh.
And that still fits with this dummy.
Yeah, so that's an interesting point. If I just restrict this from bottom, you can learn bottom, then it would no longer really correspond to disjunction. It will correspond to disjunction if I limit the conclusion to be exactly A or B. So it would certainly break, it would break a number of things, probably that isomorphism, but it would break other things as well. But we wouldn't necessarily see that by the test. Yeah, so, right, so maybe you can ask me again tomorrow, because you will see some things which can break even if the local tests succeed. Okay. Yep. Yeah. This one, right? Yes. I just was lazy and I used the X here to denote the proof and also here to denote the proof term. I overload X. Okay, yeah, we can do that. There's nothing to prevent us from saying we can apply alpha conversion. This should be lambda y, m of y. This is y. This would be y. Okay, so we can do it like that, and then we just have two different names, one for the proof here and one for this y. But we have to remember the scope of these things. We have to make sure this variable y is not used outside of this proof term. So if you remember our scopes, we can name these whatever we want. Yeah. Okay, so have fun with the homework, and tomorrow I'll teach you how to actually reason about these things so that if you get stuck in the proof and you suspect it might not be true, give you some means for proving that, yeah, it's actually not true. So far, everything is positive. You can prove something, but you can never be sure that something may not be provable. All right.